So hello everybody, welcome to your Lecture 5 skill check. Today we will be talking about a paired t-test. As you will have learned in class, a paired t-test is very much like a one-sample t-test, the only difference being the way the data is collected. And so much of what you'll see in this video will be a review of things you've seen already. But of course, as I like to say, repetition is the key to learning, so there's no harm in looking through these things again. So we'll be going back to check the conditions for using a t-distribution to do our inferences. That's essentially a review of the central limit theorem. We'll be looking at making a confidence interval and performing a hypothesis test in this scenario, looking at p-values and assessing the strength of the evidence against the null hypothesis. So here the scenario is as follows. To assess the impact of alcohol on playing strength, 50 randomly selected club chess players did the following. First, they each played a chess game against a computer opponent. Then they each consumed 2 cans of beer and played a second chess game against the same computer opponent. So a chess engine was then used to quantify the difference in the playing strength between the 2 games for each player. The mean difference in playing strength then was d bar equals minus 25.47 with a standard deviation of 76.18. Right, so let's just talk for a moment again how the data is collected. In this instance, we have our experimental units. That would be each individual chess player. And each of those experimental units is subjected to 2 measurements. One before they drink the 2 cans of beer and one after. And so each data point is a difference. For each individual experimental unit, for each chess player, there is a measured difference. And so d bar is the mean of all those measured differences. In this case, there's 50 measured differences. So we're using d bar instead of y bar to remind ourselves that we're talking about differences. And similarly, instead of using just S to represent the standard deviation of the sample, we're using S with a subscript D. And again, it reminds us that we're talking about differences. So the first question is to briefly explain why it is appropriate to use the t-distribution to compute a confidence interval and conduct a hypothesis test in this scenario. And so we just need to remember what the conditions are for that central limit theorem to be applied. So in brief, we need independence. And so individuals, in this case, on which 2 measurements are taken, one before and one after they drink the 2 cans of beer, these individuals must be independent of one another. How do we ensure that's the case? We take a random sample of chess players. These are club chess players, let's say from across Canada. And we make sure the sample size is less than 10% of the population size. In this case, the population of all club chess players. Independence then, no problem. We have that in this scenario. And then there's a large enough sample. So if the sample is large enough, then we can appeal to the central limit theorem to make the following approximation. And that is that our test statistic, our t statistic, which in this case is just the observed mean difference minus a hypothesized value divided by the standard error of d bar. The central limit theorem tells us that if the sample size is large enough, this test statistic will be approximately t in distribution, t with n minus 1 degrees of freedom. So in this case, I chose a sample size of 50, so clearly that sample size is big enough. Now, if the sample size was smaller, let's say it was sample size 10, then you would have to worry about the distribution of the individual measurements. If the distribution of individual measurements is at least symmetrical, a sample size of 10 to 15 is enough to appeal to the central limit theorem. And so we could still assume the test statistic has this t-distribution. But if the underlying distribution of measurements, so that in this case those differences, if that distribution was heavily skewed, then a sample size of 10 or 15 wouldn't be enough. We would need something bigger than 15 in order to appeal to the central limit theorem. And if it's really heavily skewed, it has to be bigger than 40. Right, so just keep in mind that as long as the sample size is bigger than 40, you don't need to worry too much. But if the sample size is smaller, and sometimes you might see cases where it's 8, 10, 15, then you have to ask yourself, what does the distribution of the individual measurements look like? So sometimes you'll be shown a histogram of those individual measurements, or maybe a box and whisker plot. Right. So in this case, at least we don't need to worry about that. So these conditions are satisfied in this case, in this scenario, and so we can go ahead and do our inferences. So second question, construct a 95% confidence interval for the population mean change in playing strength of club chess players following consumption of alcohol. What does the interval suggest? So the confidence interval here, we're taking a confidence interval for this mean difference, and it has the same form as always. We're going to start with a sample mean. This sample mean difference is our point estimate for the population mean difference. And then, of course, we go plus or minus some margin of error. That margin of error is calculated using a critical value from a t-table and the standard error of d bar. So we have our data. We have a mean difference. We have the standard deviation of those differences. We have the sample size, and we know now the degrees of freedom is 1 less the sample size. And I just want to emphasize that this symbol represents the population mean difference. Right, so you might see this phrase, population mean difference, somewhere in a MyLab assignment or on a quiz or on a test or something. So let's just try to remember that's just describing what this parameter represents. So we're making inferences on this parameter, the population mean difference. Right, so we need the critical value for this test. Critical value for this confidence interval. And so we're looking at a two-tailed probability because it's a confidence interval. We wanted to make a 95% confidence interval, and so we're looking at a two-tailed probability of 5%. And so this is the column we need to look at. The degrees of freedom is 49, and so the closest we can get to 49 without going over is 45. And so here our critical value for the confidence interval is 2.014. So here we go. We take the observed difference. This is the point estimate for that population mean difference, plus or minus our critical value multiplied by the standard error of d bar. So calculating this, we get a margin of error of 21.7, and then we can get the endpoints of the confidence interval. So fairly straightforward, I think. And now we can make a conclusion. So here our 95% confidence interval for mu bar. I just noticed that there's a funny misspelling here. That's better. So the 95% confidence interval for the population mean difference, it's between minus 47.17 and minus 3.77. What do we conclude? We are 95% confident that the true mean effect of drinking 2 beers is a reduction in playing strength of between minus 47.17 and minus 3.77. Both ends of this interval are less than 0. Hence, the data suggests that drinking two beers has a negative impact on playing strength. Good. Next question, conduct a hypothesis test at the 5% level of significance to see whether the consumption of alcohol can be said to change the mean playing strength for the population of club chess players. So you probably have seen this in 2208. Constructing a 95% confidence interval is identical to conducting a 5% two-tailed hypothesis test. And so if we were to get our critical value, we still need to look at two-tailed probability. We still have to look at this column. We have to look at the critical values that put 5% in the two tails combined. And of course, it's still 45 degrees of freedom. And so our critical value is the same, right? So this emphasizes the idea that a 95% confidence interval is very much like conducting a 5% two-tailed test. So the only difference here is now we have hypotheses, and so we have a null hypothesis that the mean population difference is 0, meaning drinking those 2 beers has no effect on playing strength. And the alternative is that it does have an effect on playing strength. And notice it's a two-tailed test, and so we're giving room for the effect of drinking 2 beers to either improve playing strength, which could be explained if you have a few beers, you might be more relaxed and you might play better. Or the other case is it actually decreases the playing strength. And so by using a two-tailed test, we're giving room for both of those outcomes. This is a picture of our test statistic. It's a t-distribution, 49 degrees of freedom. And with using our critical value, we can define the places where we will reject the null hypothesis. And so these two tails, 2.5% in each one, if our test statistic falls into either of those two tails, we will reject the null hypothesis. Of course, in between those two tails is our 95%. Right. So our decision rule is we will reject the null hypothesis at the 5% level of significance if the critical value in absolute value is bigger than, sorry, I said that wrong. If the test statistic here in absolute value is greater than the critical value. So that just is a way of saying we're going to reject if our test statistic is either in the lower tail to the left of this critical value or in the upper tail to the right of the positive value, the positive critical value. Right, so now we just do the calculation. Our test statistic, as always, it's the mean, the observed mean value minus what we hypothesize under the null, divided by the standard error of that mean value. So we can plug our numbers in. We have minus 25.47 as the observed mean value. The null hypothesis, under the null hypothesis, the population mean difference is 0. And down here we have our standard error of d bar. So it's the standard deviation of the data divided by the square root of the sample size. And so we get our test statistic being minus 2.3641. Right, so that test statistic, clearly this test statistic is in the lower tail, and so we're going to reject the null hypothesis. And notice this is consistent with the confidence interval. Looking at our 95% confidence interval, we notice that confidence interval, both ends of that interval were less than 0, which is suggesting that the population mean difference in playing strength after drinking 2 beers is negative. In other words, the playing strength was reduced. Here we basically get the same conclusion. So here we're going to reject the null hypothesis at the 5% level of significance because our test statistic is less than the leftmost critical value. And we can further say that our test is suggesting that the impact of drinking those 2 beers is a reduction in playing strength, in the average playing strength. So finally, we're going to look at the p-value of our test statistic, and we're going to describe the strength of the evidence against the null hypothesis. And so there's 2 ways to do this. The first way is to do the estimation. Now, before we do that, I just want to review again what p-value means. And so in this case, it's a p-value for a two-tailed test. And what is this? It is the probability of getting a test statistic as far from 0 or further than what was observed, assuming the null hypothesis is true. Right, so if the null hypothesis is true, this t-distribution is sort of representing the distribution of our test statistic. If the null is true, and if we put our test statistic here and here, let's just see what, here's the test statistic. So if we put minus 2.3641 down here at the lower tail and the positive value in the upper tail, then the area in those 2 tails combined would give us the p-value for the test, would give us the probability of getting a test statistic as far from 0 as what we observed or further. Right, so how do we find out what that p-value is? Well, we can only estimate a range of values. Again, we're looking at two-tail probability. We notice that our test statistic is between these 2 numbers, and that therefore we can conclude that our p-value, at least in approximation, is between these 2 numbers. It's between 2% and 5%. So the p-value bigger than 2%, less than 5%. This, of course, is approximation because we're using 45 degrees of freedom when we should be using 49, but it's a very good approximation because the sample size is quite large. So we can conclude that the evidence against the null hypothesis is moderate. So let's take now a quick look at the Minitab. What I'm going to do first is I'm going to show you how you could use Minitab to do this test. So we go into statistics, STAT. We're going to pick basic statistics, and in this menu we can pick a one sample t-test. Well, we could pick a paired t-test, or we could pick a one sample t-test. They're actually going to be the same. And the reason they're going to be the same is I'm just going to use the summarized data. So the summarized data here, we need the sample size, which was 50. Whoops, 50. The sample mean was minus 25.17, I think. Let me double check that. It was minus 25.5. Okay. And I see the sample standard deviation is 26.2. So we're going to plug those in. So 25.5, 76.2. Let me double check once more to make sure those are correct. 76.2, 25.5. Good. Sample size of 50. Okay. So we put these values in. This is the summarized data. Let's see the options. We're going to have as an alternative hypothesis that the difference is not equal to what was hypothesized, and the hypothesized difference is 0. The confidence level is 95%, which is the same as specifying a 5% level of significance. So I think this will do it. We just press OK. Yeah, and here is the output. So this is the same output that I have on the slide, which I will show you now. Right, so let's go to this slide. And so what do we see? Look, we have our sample size, we have our sample mean and standard deviation. What is this value? This number is the standard error of the sample mean. And how do you get that value? Well, if you were to compute it, you would just take the standard deviation from the sample, divide it by the square root of the sample size. So let me just show you so that you can be completely convinced of this. So if we take 76.2, that's the sample standard deviation, divide by the square root of 50, that gives you 10.8 basically, which is what we have here. And so this is the standard error of the sample mean. So essentially Minitab gives you that if you needed it for some reason. Let's see. So go back. Right, and I just want to point out that the 95% confidence interval for the population mean difference is here, and that is in agreement with what we calculated. You can see that the test statistic for this test is in agreement with what we calculated. And now the p-value also just validates our range of values. So we said the p-value was between 2 and 5%, and you can see it's about 2.2%. Right, so this determining the range of values for the p-value using a table isn't so bad. It isn't too far away from what we would get. At least in this case, it's not. Right, so that is the end of the show. I would say thank you for listening. I hope you found this useful, and we'll see you next time. Bye-bye.